Alright class, the last topic for Unit 5 is modeling. A common difference is the differences of the consecutive y values when the x values in the data are evenly spaced. And a common ratio is that the consecutive y values are multiplied by some ratio when the x values are evenly spaced. So the key here is make sure the x values are evenly spaced, but I probably won't give you one that's not. So clearly you can see that between each x value it's just going up by 1. So the x values are evenly spaced. And then you have to look at the data and go, what's happening? If you can see it, it's going -2 to 2 to 6. So from here to here it's +4, +4, +4, +4, +4. So we have a common difference between all of the terms, and I'm going to call these the first differences. So when the first differences are constant, we have a linear function. So okay, so that's what happens. You have common first differences when you have a linear function. Let's look at a quadratic. Again, we have common differences are at the top, so it's evenly spaced. Now we're going to look at the different, well, first of all, is it being multiplied by anything? No, because it's all different. So we're going to look at the differences. That's down 1, that's up 1, that's up 3, that's up 5, and I wrote 3. That's up 7. We don't have a common anything here. However, now let's look at the difference between these values. -1 to +1 is up 2. +1 to +3 is up 2. +3 to +5 is up 2. And +5 to +7 is up 2. So what do we notice? The quadratics have second differences that are common. Okay. Let's look at a cubic, and hopefully you guys guess that maybe the difference level will be the third level where it's common, but let's check anyway. This is +1, this is +1, this is +7, this is +19, and this is +37. So that's the first level. The difference between these two is 0, 6, 12, and 18. So now I can do the difference between the second differences, and that's up 6, and up 6. So the difference level of equality equal to the power of the function. So again, we notice that the third differences are constant. Okay, so that's the cubic, quadratic, and linear. Now we're going to look at exponential and what happens. So an exponential function, again, we have an evenly spaced top, but you don't, the common differences don't happen here. With an exponential, you have to look at multiplication. 1.5 to 3 is times 2, times 2, times 2, times 2, and times 2. So what you notice is that exponential has a common ratio and that's going to equal its base because the base number was 2 for the exponent. Okay, so let's look at a couple of these. First thing you should check to see if it's being multiplied. Okay, and then if it's exponential, find the common ratio. Okay, so 0.5 to 1 is times 2, times 2, times 2, times 2. So we can clearly see that this is exponential. And the common ratio is 2. Okay? Over here, 2 times 0 is 0. 0 times nothing gets you to 2. So this is not exponential. So we have to look at the other ones. Now, notice it is still evenly spaced even though they go by 2's. That doesn't matter as long as it's evenly spaced for the x's. So this is down 2. That's up 2. That's up 6. That's up 10. That one is up 14. And this one's up 18. So it's not a linear. This is plus 4, plus 4, plus 4, plus 4, plus 4. So this is a quadratic. We look at this and see that it looks like, it's hard to see here, but it looks like it's being divided by 3. Or you can think of that as being multiplied by 1/3. So times 1/3, times 1/3, times 1/3, times 1/3, times 1/3. So this again is exponential. And the common ratio is 1/3. Okay. And then we'll do this one. Evenly spaced on top. No, doesn't look like multiplying is working there, so I'm going to just, this went up 8. This went up 8. This one, this changed from what I had before, so hold on one second. So 69 minus 13 is 56. $221 minus 69 is 152. And then 296. So clearly it's not linear. 0, 48, 96, and then 144. So it's not quadratic. 48, 48, 48. So this would be a cubic. Okay. Now these are a little different. This is like solving a little system here. I want to come up with this based on these 2 points. So the first thing I'm going to do is plot both these points. I'm going to write both equations down. So I know y is equal to 6. I don't know what a is or b is, but I know x is to the first. So I know that equation. I also know that when y is 54, I get a times b to the third. Okay? It's really easy to solve for a here on this one by dividing by b to the first. So I could say that a is equal to 6 divided by b to the first. Okay? Then I can take this and sub it into this second equation over here. So the second equation is 54 equals 6 over b to the first times b cubed. Well, b cubed divided by b to the first is b squared, so we get 54 equals 6b squared. And then you divide by 6 times 9 is 54. So you get b squared equals 9. B equals 3. Because remember, b has to be positive for an exponential function. It should be plus or minus, but we don't want the negative one. So if b is 3, you plug it back into the original. We get a is equal to 6 over 3 to the first, which is just 2. So now I can look back here and rewrite my exponential function. Y equals a, which is 2 times 3 to the x. Okay, so that is my exponential function. We can do it again. Start with the 2 equations. So I have y is equal to a times b to the second, and I get y, nope, that's x I wrote down. 24 is equal to a times b to the third. I'm going to solve for a here. A is equal to 12 over b squared, and then I'm going to plug that into this equation here. When I do that, I get 24 is equal to 12 over b squared times b cubed. Well, I have a b cubed on top and a b squared on bottom, so it ends up being 24 equals 12b, which means b equals 2. Then you plug that one in here. A is equal to 12 over 2 squared. A is equal to 3. So it kind of switched from the one we just did. So my final equation is that a equals 3, b equals 2, and that's to the x. Okay, so that's solving a system. Alright, we're revisiting our 4 formulas from the first quiz. We have a growth and decay model, and then with interest, we have those. We're going to actually solve these without using our calculators now, though. We're going to use logs, the properties that we learned for the second quiz. So the value of a motorcycle in thousands of dollars is this model here, where T is the number of years since the motorcycle was new. Identify the original value when it was new and the annual percent increase or decrease. Well, again, this value is 1 plus or minus something, and since it's less than 1, it's 1 minus r equals 0.9, so r is equal to 0.1. And this is the starting amount. So the original value is $18,000, and it's a decrease is 10%. Estimate when the value will be 13,000. So now I want to know when y is 13 because we're in thousands. 18 times 0.9 to the t. So here's what you do. You want to get the law or the exponential function by itself. So we're going to divide by 18. So those go away, and you get 13 over 18 is equal to 0.9 to the t. So when we solve these equations on the quiz that we just took, you needed to either log or natural log both sides. So I'm going to natural log both sides, and you get the natural log of 13/18 is equal to t times the natural log of 0.9. It's a times. So, because remember, when you natural log, you can bring the t down. So that means that t is equal to the natural log of 13/18 over the natural log of 0.9. And when you type that all in, you get it's approximately 3.089 years. And we did not have to use our graphing anymore. That's what logs let us do. They let us solve these problems without using the calculator in terms of graphing. So, in 2005, we have a population was 1.3 million. During the next 10 years, population increased by that percent each year, which if you put that as a rate, that's 0.0125. Write an exponential model given y and t, so y is equal to, the starting point in millions is 1.3. 1 plus, because it's increasing, 0.0125 to the t. So if I rewrite that, I get y is equal to 1.3 times 1.0125 to the t. And I wrote 2. So that is my equation. Estimate the year when the population was 1.4. So I'm going to put a 1.4 on this side, a 1.3 still on this side. I still have the 1.0125 to the t. So again, we have to solve this. The first thing you have to do, though, is get rid of the thing in front. So I get 1.4 over 1.3 equals just the exponential piece. Now I can natural log both sides, and the t will come down. So I get the natural log of 1.4 over 1.3 equals t times the natural log of 1.0125. And now, since this is a number, you divide by that. So t is approximately, well, it's equal to first the natural log of 1.4 over 1.3 divided by the natural log of 1.0125. No, you cannot like cancel anything, just type it in as is. You get the t is approximately 5.966. It's not quite 6, so since it says when, the year, it happens 5 years in, which is at 2000, almost 2006, or 2010. So it's almost 2011. But it happens during 2010. Okay. Now we have banking problems. We decide which formula we're going to use. Josie invested $500,000 that earns 1.2% annual interest, compounded continuously. So that's this formula. Okay. How long will it take to reach 600,000? So I know my final amount is 600,000. I know my initial amount is 500,000. I know it's E times 0.012 t. Again, this is just like the problems up above. We have to solve, but before you do that, or we have to natural log both sides, but before we do that, we have to divide. Okay, so we get 6/5 is equal to e to the 0.012 t. Now you can natural log both sides, just like we were doing before. The nice thing about this whole thing comes down, and we get natural log of 6/5 is equal to 0.012 t times the natural log of e, but you guys should know that this is equal to 1. So now all we have to do is divide by 0.012, so t is equal to natural log of 6/5 over 0.012, which means it'll take 15.193 years. Okay, so these last three problems, all we did was we went back to the first quiz, and instead of solving with our graphing calculator, we now solved using the natural log method that we learned in the second quiz. So, hope you guys understood that. This was the last lesson for this unit.